Sheet for 1.3, the mole review. We're just down to the last leg. On to question 24. Now, we did this one in class, so I am going to go through this one a little bit more quickly than I normally would. I am going to try to explain all the steps, but I'm going to be a little bit cavalier with my pace. All right, so what do we got? We got yeast eat glucose, okay, and that's a molecule for glucose. And they produce energy just like us. And they also produce carbon dioxide as a byproduct. And we utilize this to make bread rise, and the total reaction is right here. So we're asked to balance the reaction first. And we're asked to determine the volume of oxygen at STP that the yeast will produce, that they will require if they want to eat 403 grams of glucose, sugar. Okay. So that looks like we're converting from oxygen to glucose to oxygen. So in our conversions, we're going to make sure to include the value we're given, but first we're going to balance the reaction. I'm going to go through this pretty quickly because we went through it already. So I would choose an element that only shows up maybe once or twice. So it looks like I can see 2 instances of carbon. 6 carbons here, but there's 1 here. So I can put a 6 in front of the carbon dioxide to balance the carbons. Hydrogen, there's 12 here and 2 here, so I can put a 6 here to balance the hydrogens. And we went over the argument for why there's a 6 in front of this oxygen in class. I'll let you, if you missed class today, go through that a little bit more slowly on your own. And if you're not sure, we're going to be practicing that again in question 25. Okay, so that's a balanced reaction. There's 6 as a coefficient in front of the last 3 terms. All right, and next we're going to be converting glucose into a volume of oxygen that's required. Okay. So I'm going to start by writing down that we have, pardon me, I'm just going to fix my workspace here so that I can see the question and also write some information down. All right, so question 24. Perfect. All right, so I've got 403 grams of glucose. I'm going to just abbreviate that GLU so I don't have to write out the entire word or the atomic, the molecular, it's been a long day, the molecular formula every time. All right, cool. So 403 grams of glucose. Now, I mentioned the other day that this is my favorite molecule, so I know there are 180 grams for every mole because this one I've just got memorized. First thing I want to do, if I want to convert it into a volume of oxygen, is I need to go over my mole bridge. So I'm just going to say I've got 1 mole of glucose for every 180 grams of glucose. And okay, that's fine, but I want to convert it into moles of oxygen. And that's why we balance a reaction. This tells us how many moles of oxygen are consumed for every mole of glucose. It says 1 mole of glucose for every 6 moles of oxygen. So I can say 1 mole glucose here to cancel out with the mole of glucose. That gives us 6 moles of oxygen. Good. And then that's not all, though, because I wasn't asked for how many moles. I asked for the volume of oxygen at standard temperature and pressure. So I know that at standard temperature and pressure, every gas occupies 22.4 liters for every 1 mole that it has. So I've got moles of oxygen canceling out. I've got liters of oxygen. And so now all I have to do is punch that in. I get 403 times 6 times 22.4. That's divided by 180. And I get 300. Or actually 301. Is that the right sig figs? I think it is 3 sig figs. Okay, so we get 301 liters of oxygen, which is not an insignificant amount of oxygen, I think you'll agree. All right, cool. Moving on to question 25. We're going to go through this one a little bit more slowly. All right, so this is an interesting reaction as well. We also use yeast to make drinking alcohol, ethanol. So all we do there is if we don't provide them with oxygen. This is the only difference really between making bread and making beer or wine or cider. All right, so what do we got here? So we've got ethanol being produced. Okay, so maybe that's relevant. And a lot of this is just information you may want to know about yeast because yeast are pretty important to our lives. All right, and then what else do we know? We want to balance the reactions. That's what we're asked for. And so we'll balance the reaction and then determine the mass of sugar we'll need. If we want to brew 1 liter with a certain concentration of ethanol, which is actually about 5% ethanol if you convert it, which is about the concentration of a beer. A typical beer. All right, so first things first, we're going to balance the reaction. Okay, this looks a little tricky. Organic reactions like this are always a little tricky to balance. All right, so I'm going to start with the thing that shows up the fewest number of times, which I see is hydrogen. 12 here and 6 here, so I'm actually going to put a 2 right there. All right, I'm going to move on to the carbons now. Oh man, I really hope this balances nicely. All right, so this actually looks like it could be messy. I've got 6 carbons on the left. I'm going to write that down, 6 carbons. I've got 4 carbons here, two C2s, and 1 carbon there. Actually, it's not so bad. So I've got 5 carbons on the right, 6 carbons. So if I just put a 2 here instead of just that 1, I've got 2 carbons. Now the carbons are balanced. I really hope the oxygens have been balanced by doing this. So I've got 6 oxygens here, 2 oxygens here, and 2 O2, so that's 4. Hey, look at that. We're balanced. That was a lot less painful than I thought it would be. All right. Okay, so now we can start solving. So I've got a big capital M, so I remembered that I need to turn that into moles per liter every time I see that. Okay. And I've got a liter. So a liter of beer. Okay. So what I'm going to start by doing is I'm going to start by saying, okay, that's the quantity of beer I have. So I'm going to start with that specific value, 1.00 liters. Now, what am I asked for? The mass of sugar. What sugar are we talking about here? Glucose. Just like us, they eat glucose. Yeast, because actually yeast are very closely related to us, and we use yeast as a model organism in labs for humans all the time, believe it or not. All right, so we want to know the mass of glucose, really. All right, so to do that, we're going to start by, so 1.00 moles, or liters, and we're going to turn that into a number of moles of ethanol. All right, and so I'm going to use the molarity, 0.858 moles of I'm going to write that C2H6O over 1 liter of solution. All right, and now I need to know, okay, well, how many moles of ethanol do I get for every mole of glucose? And it looks like it's a 1-to-2 ratio. And so that says, okay, well, I can have, what do I want? I want to know, to convert moles of ethanol into moles of glucose. So I know that it looks like 2 moles of ethanol, C2H6O, convert into 1 mole of glucose, and I think I'll just write that as GLU, like I did in the last question. I could have written the simple form of ethanol here, ETOH, but I didn't want to introduce too much notation. I used glue in the last one, so I'm going to continue to do that. All right, and that's not all. We need to know the mass of the sugar, so we need to convert the number of moles into a mass. And we talked in the last question about how the molar mass of glucose is 180 grams for every 1 mole. So we're just going to use that value again, 180 grams of glucose for every 1 mole of glucose. All right, and what does that give us? Let's see. To make a liter of beer, how much sugar do you need? 1 times 0.858 times 180, and we're going to divide that all by 2. So to make a liter of beer, it's going to require 77.2 grams of glucose, C6H12O6. And that is typically found by isolating sugar in maltose form, from barley. And that's why barley is used to make beer, to isolate the sugars from the barley. Okay, let's move on. Let's talk about the Saturn V rocket, my favorite rocket. All right, so let's move on. Saturn V used liquid oxygen and liquid hydrogen, amazingly, as the fuel for the second and third stages of launch. And we have a certain reaction, which is useful. It looks like it's balanced, which is nice. And it uses 1.2 million liters of liquid oxygen. And the question is, okay, how many grams of water did it produce if the density of liquid oxygen, it's another given here, so I'm going to use green. Density of liquid oxygen is, it's a little bit more dense than water. Water is 1 gram per mil. Okay. So we should start 26 by listing any values that were given to begin with, specific to the Saturn V rocket, which is the 1.2 million. So I'm going to write million as times 10 to the power of 6 liters, which is a tremendous number of liters. All right. And I need to find out how many grams of water. Oh, so I should probably include that's oxygen. Liters of oxygen. All right, so I can turn that into a number of, so I can turn it into grams and then maybe into moles, so I can convert between moles of oxygen to moles of water. But before I do that, I should probably turn this number of liters into a number of milliliters. So I'm going to divide that by 1,000. So I know that 1 liter of oxygen, I guess I times it by 1,000, is 1,000 milliliters of oxygen. And now I can use this density. I can convert it into a mass. It says 141 grams of oxygen for every 1 milliliter of oxygen. But of course, we always want to get to moles when we're ever doing questions like this. And so we're going to need the molar mass of O2. And the molar mass of O2 is 2 oxygens. Where's my periodic table got to? It's under all this paper. Oxygen is a molar mass of 16.0 grams for every mole. So 2 oxygens is 2 times that. So 2 times 16.0 grams per mole, which is 32.0 grams per mole. All right, so now I can use this to convert the number of grams into a number of moles of oxygen. All right, so I can say 1 mole of O2 is going to convert 32.0 grams of O2. And now I can use my molar ratio. I can convert moles of oxygen. Looks like there's 1 mole of oxygen for every 2 moles of hydrogen produced, for every 1 mole of oxygen consumed. So 1 mole O2 is going to make 2 moles H2O. Whew. Almost done. I also need actually the molar mass of water, because we're asked for how many grams of water does this produce. So, okay, let's find the molar mass of H2O. It's going to be easy because molar mass of hydrogen is 1. So for hydrogen, I've got 2 times 1.0 grams per mole. And oxygen is 116.0 grams per mole. So overall we get 18.0 grams per mole. All right, and now I can convert the number of moles of water to grams of water. 18.0 grams H2O for every 1 mole H2O. And you can see this gets pretty heavy. There's a lot of terms, so many that I might actually need to zoom out to see them all. There we go. Still a little tough, so I'm going to start here. All right. So I've got 1.2 times 10 to the power 6 times 1,000 times 1.141 times 2 times 18. And that's all going to be divided by 32. So that's, oh wow, it's a lot of water. Holy cow. All right, so this all equals how many sig figs should I have here? 1.2. Okay, so I've got 2 sig figs, so it's 1.5 times 10 to the power of 9 grams of water. Actually, kind of like kilograms if I'm thinking about water, because I can convert that to liters really easily. So I'm going to actually say it's times 10 to the power 6 kilograms of water. 1.5 kilograms of water, or 1.5 million liters of water. All right, so I'm going to put a box around this one, though. These are for my own contextualization. Either of these are fine. All right, great. Oh, rocket science. Hard. All right, we've got a few more to finish us off. So, okay, we've got a question about Mac watching Breaking Bad, and he tries to make thermite to melt some stuff. Thermite just happens to release tons of heat energy, very exothermic. And so we've got a reaction here that's given and useful. All right, so Mac is going to get the aluminum by grinding up a 14.9 gram pop can. So that's the aluminum. And the question is, how much iron oxide will Mac need to weigh out, to react with all this aluminum? Okay, actually doesn't look so bad. Let's find out. Right, so what do we have here? We have 14.9 grams for our pop can. 14.9 grams. And that pop can is aluminum, so I'm just going to abbreviate it as Al. Now, obviously, we need to be able to convert into moles eventually, so I'm going to use my molar mass of aluminum to convert the grams of aluminum into a mass of aluminum, which is 27.0 grams per mole. So 27.0 grams of aluminum for every 1 mole of aluminum. And then I can look at the molar ratio of aluminum to iron oxide. It looks like 2 moles of aluminum are needed for every 1 mole of iron oxide, or iron 3 oxide, I should say. And so I can say, well, that means 2 moles of aluminum for every 1 mole of iron oxide. Okay. Wait, what was I asked? How much? So actually, how much does he need to weigh out? So you can't weigh out moles because your scale doesn't measure things in moles. We're going to need to turn that into a mass. To do that, we're going to need the molar mass of iron 3 oxide. Okay, iron 3 oxide, so it's going to have 2 irons. So that's going to be, iron is 55.8 grams per mole. So it's 2 times 55.8 grams per mole for iron, and there's 3 times oxygen, which is 16.0 grams per, 3 times oxygen, mole, and okay, so what does that give us? 2 times 55.8 plus 3 times 16. I get 100, and that's lighter than I thought. 9.6 grams per mole for iron oxide. So now I can use that to turn that into grams after 9.6 grams for 1 mole of iron oxide. And we'll also put that there. Okay, we'll cheat. And so that tells us the mass Mac needs to weigh out. Let's find out how much that all adds up to. So we got 14.9 grams of a pop can times 159.6. And we're going to divide that all by 27 and divide it again by 2. So what do we get? We get 44 grams, 0.0, I guess. Looks like we got 3 sig figs grams of iron 3 oxide. And that'll be the right molar ratio to convert it. I don't feel bad about putting that information out there because this is incredibly difficult to light, having tried to do this as a science experiment myself. I don't imagine you'll have a lot of luck, even if you tried that. All right, moving on to a safer reaction, 28. Stomach acid, okay, cool. We've got, so okay, maybe it's relevant that we're talking about acid. And you can neutralize stomach acid with milk of magnesia, which is why you drink it. And we're given this balanced reaction here. Okay, not so bad to balance. And the question is, how many HCl molecules can be neutralized? Okay, how many HCl molecules can be neutralized by drinking 50 mils of a 4.12 molar magnesium hydroxide solution? And we got to remember that 4.12 molar is 4.12 moles for every liter. Every time we see a capital M like that, we should probably convert it. All right. So we should start with the specific thing. We're taking a 50 ml dose today, and maybe we'll take a 100 ml dose tomorrow. Let's see how many molecules of hydrochloric acid we can neutralize. So 50 mils. Okay. Now, how can I do this? Maybe I'll try to fold this a little bit. All right. So 50 mils. However, the molarity of milk of magnesia is in moles per liter, so we should probably convert that to liters. What do we have? 1 liter is 1,000 mils. Okay. And now I can convert. Oh, I should probably be writing magnesium hydroxide. Well, I won't do that until I'm finished. Okay, I'll put that in this conversion here because the entire solution is not magnesium hydroxide. It's important to remember. However, it does have 4.12 moles of magnesium hydroxide for every liter of solution. So 4.12 moles MgOH2 every 1 liter. And now I see, okay, well, for every mole of magnesium hydroxide, that neutralizes 2 hydrochloric acid molecules, assuming that it is 100% effective, which it is definitely not. All right, so that means we have a molar ratio of 1 mole MgOH2 neutralizes 2 moles of HCl. Great. But we're asked how many molecules, so we got to convert moles into molecules. So the last step is we're going to use Avogadro's number. So 6.02 times 10 to the 23 molecules of HCl for every 1 mole of HCl. And then we're done. All right, so we'll put into a calculator here. We've got 50 times 4.12 times 2 times 6.02 times 10 to the 23. That's a big number. All right, and we're going to divide that by 1,000. So a lot of HCl molecules. So we get 2 point, how many sig figs? 1. Okay, so 2 times 10 to the 23 HCl molecules. I'll put that in a little big box. All right, last question. We made it. 29. All right. So it's an interesting property of aluminum that it can be totally disrupted with hydrochloric acid. So this is like a combination of the last two questions. Max Thermite question involved aluminum can, and the next question involved hydrochloric acid. So it makes me wonder if you know what, I'm going to save that wonder for another time. All right, let's just get on with this. So what do we got here? You can disrupt aluminum with hydrochloric acid. This is the reaction. Looks like it's balanced, which is nice. And let's see, the mass of an aluminum pop can is 14.9 grams. Okay. We want to know what is the theoretical volume of a 0.1 molar solution that you'd need to dissolve the entire can. Okay, so we know we have some amount of 1 molar solution, which we should convert into 1.011 moles of HCl for every 1 liter. We've got to remember that's what that means. This is 0, in case it wasn't obvious. All right, so we should start with the can. That's the only thing we're really given. 14.9 grams of aluminum. All right, and we're going to convert that into, well, we've got to go to moles always, and we're going to eventually convert that into how many moles of hydrochloric acid we're going to need. And then we'll have to figure out the volume of the solution we're going to need to measure out. Maybe we can try this in class. I've done this before. All right, let's do this. So what do we got? 14.9 grams of aluminum. All right, so to convert that into moles, we're going to need the molar mass of aluminum, which we saw in an earlier question, is 27.0 grams for every mole. So I want my grams of aluminum down here to cancel, so that's 27.0 grams for every 1 mole of aluminum. Okay, and that's moles of aluminum now. I can convert moles of aluminum to moles of hydrochloric acid. And that says that for every 2 moles of aluminum, that it consumes 6 moles of HCl are also consumed as reactants. All right, and so that's fine. No number of moles. I need to convert that into a volume, which I can use the molarity for. And that says that 1 liter of solution, maybe I'll just write solution, is equivalent to 1.00 moles HCl. All right, moles of HCl cancel, moles of aluminum cancel, grams of aluminum cancel, and I think we're good. All right, so let's just punch that into a calculator then. We got 14.9 times 6. That's going to be divided by 27. We'll also divide it by 2, and we'll divide it by 0.1. It looks like we're going to need 16.5 liters. That's a lot, 16.5 liters. So I think maybe if we're going to do this in class, we'll need a more concentrated solution. That way we don't need as large a volume of 0.100 molar HCl solution. And there you have it. All right, well, happy studying. Ask me for any questions. I'll be available for FlexBlock. Good luck.